Okay, you guys, we're going to be studying what happens when you add light, different colors of light together. And so I'm wearing my lab coat. I hope I look official. Well, thank you. All right. So I'm going to show you what I have here. I have 3 different lights that are set up to switches that can control the amount of current that flows through, so the brightness of them. Over here, there's a blue light. In the middle, there's a red light, and here's the green light.
Kind of hard to see.
You'll be looking at just the reverse, so we'll just start with the blue light. So we'll shut the others off. So we have a white screen, I have a white lab coat, and you can see the umbra, and on the very edge, the penumbra. It's a fuzziest shadow, and the screen is white. No, it's blue. Is my lab coat kind of blue? Sort of. Yeah, bluish. So what happens if we add one more color? What happens if we add green, let's say? So let's see. Whoa. All right, so we see an umbra, well, it's kind of actually a penumbra, a blue, and a penumbra of green, and an umbra of black. Interesting. So the blue is illuminating the part that's shadowed by the green, and the green is illuminating the part that's shadowed, that the blue is shadowed by the hand. Anyway, and what's the screen color? What's kind of a bluish green color? We call that cyan, C-Y-A-N. But it's kind of hard to see, I think, looking in the middle here. It's easier to see the cyan than elsewhere. But what happens if we take out the green and add red? Here's the blue screen. Whoa. Whoa, look at the combination on the screen. That is called magenta. Well, sort of. You'd have to ask an art teacher. But anyway, and the shadows. Notice we have the penumbra of blue because the red is being shadowed out or shaded out by the hand. And then over here we have red because the blue is being shadowed out by the hand. But when you combine those 2 colors, you have magenta. So with blue and green, you have cyan. With blue and red, you have magenta. So what if, and we're adding light together. So we're not subtracting out any light, we're just mixing them together. What do we have left? What if we mixed all 3? What would happen? So it's hard with our situation to have it really mixed because they're cleaning the room and my lights are a little closer than normal, but really that screen, well, okay, it looks kind of bluish green, but it's a lighter color. And when you add all 3 of those colors together, you get white light. That's what we really ought to be seeing if these weren't so close to the screen. But let's take a look at shadows. Wow. So there you see the red and the green and the blue, but you also see cyan right here and yellow and a little magenta over here. And then the umbra, where all the light is blocked. And this could be a good shadow show. In fact, if we were in class, I would have someone else being our model, and they would, I would ask them to tell us a story. Get out of my room! No! Yes, or I'm gonna tell Mom! Yeah, whatever. Okay. So that's mixing color by adding colors of light, different frequencies of light together. When you add those three colors together, and by the way, we call these the primary colors of light, so blue, red, and green. And when you mix them in the order that we did, and we see the results here, you end up having the complementary colors. So yellow is a complementary color, magenta is a complementary color, and cyan is a complementary color. And what that means is when you take out one of the complementary colors, you end up, let me think about that for a second. When you mix two of them together, yeah, you end up seeing the other primary color. So when I've got the yellow and the cyan and the magenta all mixed, I get, we'll have to think more about that. I'll let you think about that. How does it go? Now this is different than doing pigments. Pigments are things like, okay, I have a block that I painted red. Does it look red? Yeah, it looks pretty red because the combination of these three primary lights produces white, and the red frequency is being reflected here, whereas the green and the blue frequencies are being absorbed. So the only reflected frequency is the red. And if I take green, it looks green. Once again, we have all three colors. So in this case, the red is being absorbed, the blue is being absorbed, and the green frequencies are being reflected. So we see green, and so on it goes. And if I get the blue out, I think this one is blue, yeah. I get the blue out, again you can see under white light, the blue frequencies in the light are being reflected, whereas the green and the red are being absorbed. So we see it as blue. So what would a yellow block look like? Well, it looks pretty yellow.
Mm-hmm.
That's because it's being hit with white light, a combination of all three primary colors. But what would it look like if we took out the red? I wonder what. Well, it still looks pretty yellow. I wonder what would happen if we took out the blue. Well, we know what would happen if we took out the green. We wouldn't see anything at all because it'd be pretty dark. So, I don't know if you can tell by my skin color, but I look kind of, do I look scary? I mean, a lighting person in drama, I mean, if they were the stage lighting controller, they could really affect the sensation that the audience gets. And by adding red light, what happens to what the appearance of the actors or actresses look? How do they look? And the reds, and the greens. So anyway, the addition of colored light has a big impact on what we see. So I hope you enjoyed that, and I know I've given you an article to read about primary additive colors and subtractive colors. Remember, anytime you talk about subtractive colors, you're talking about a color being subtracted out, so you don't see it. So like I have a blouse underneath this long sleeve blouse, and this is orange. And in white light, it looks pretty orange. But if I change the colors, it would change this. Right now, yeah, a lot of different frequencies are being reflected, and that's why we see orange. But some of them are being absorbed. If I was wearing black, black appears black because it's absorbing all the frequencies. And what happens when it absorbs the frequencies? Well, if I walked outside, today it's a nice sunny day, if I walked outside wearing black, what would happen to me? If I'm wearing white, well, all the frequencies are reflected off. But if I'm wearing black, I'm just stepping through the darkness, looking for my sweatshirt. Hold that for a second, don't pause, wait for it, wait for it.
We could have a little light show.
Okay, if I'm wearing black, I'm absorbing all the frequencies of light, and what happens is we don't see any color. But what happens to me, I have some maroon and gold, but anyway, what happens to me is I'm feeling more warmth. So the transfer of energy from the light waves and the absorption of those light waves convert to thermal energy, and I get hot. So that's why in cultures that live more towards the equator, you'll see them wearing a lot of white, whereas cultures that live north of the equator and south of the equator, you might see them wearing more black. But there are other problems with wearing those colors, because black might be a good absorber of light, but it's also, back to our study of thermodynamics, we didn't really talk about this a ton. We had some cans of different colors, but the darker the color, the more it will emit infrared radiation. So the best thing to do would be, I'll let you figure out what the best thing to do is, because you have a lot of life experience in a pretty moderate climate that we have here in Scotts Valley. But I hope you enjoyed the different combinations of, and the addition of different frequencies of light. All right.